The journey of neural networks commenced with the advent of machine learning, a subfield of artificial intelligence focused on enabling machines to learn from vast amounts of data. During the 1950s and 1960s, pioneers such as Frank Rosenblatt introduced the perceptron, a simple neural network model designed to classify inputs into one of two categories. This innovation laid the groundwork for future research by demonstrating the computational potential of networks modeled after the human brain. Despite its promises, the perceptron faced limitations. Notably, it struggled with tasks that were not linearly separable, a challenge highlighted in Minsky and Papert's 1969 book. This critique stalled further progression for several years until the resurgence of research in the late 1980s. The shift towards deep learning. Entering the new millennium, advancements in algorithm design, computational power, and data availability catalyzed a significant evolution in neural networks. Researchers began developing multi-layer networks, soon known as deep learning architectures. These models promised and delivered improved performance by introducing layers of abstraction, which enabled the capture of complex patterns within data. A key development was the backpropagation algorithm's refinement, providing a practical methodology for adjusting weights in a multi-layer model. Another milestone involved convolutional neural networks, which excelled in image recognition tasks. These accomplishments marked a departure from earlier constraints, where the deep learning paradigm triumphed over traditional methods in various domains. Neural networks in modern AI. Today, neural networks are an integral part of modern artificial intelligence systems, tackling diverse and intricate challenges. They drive innovation in automated healthcare diagnostics, autonomous vehicles, and natural language processing. For instance, generative adversarial networks, GANs, have showcased stellar performance in creating realistic images, while recurrent neural networks handle sequential data with remarkable efficiency. As neural network models continue to mature, their application expands further into unexpected areas, harnessing the collective power of massive datasets and sophisticated algorithms. Thus, the evolution from basic perceptron models to advanced deep learning architectures exemplifies the dynamic growth trajectory in the field of artificial intelligence. Basic concepts of neural networks. Understanding artificial neurons. Artificial neurons are the foundational elements of neural networks, akin to biological neurons. Each neuron receives input, processes it, and generates an output. This output is then transmitted to other neurons. Mathematically, this can be expressed as a weighted sum of inputs. Y equals sum W_I times X_I plus B, where X_I represents the input signals, W_I denotes the weights, and B signifies the bias. The weights adjust the strength of the inputs, facilitating learning by changing through iterative processes. Artificial neurons enable networks to capture complex patterns in data, forming the cornerstone for advanced architectures. Activation functions. Explained activation functions determine the neuron's output, deciding whether it should activate. They introduce nonlinearity, allowing the network to tackle intricate problems. Common activation functions include the sigmoid, hyperbolic tangent, and rectified linear unit, ReLU. The sigmoid function compresses output into a range between 0 and 1, which is advantageous for binary classification tasks. However, it suffers from gradient saturation, reducing learning efficiency. The hyperbolic tangent function, meanwhile, offers outputs between 1 and 1, enabling better model convergence. ReLU, a more recent addition, outputs the input directly if positive, otherwise, it returns 0. It addresses issues of gradient saturation, making it the preferred choice for many deep networks. The importance of layer architecture. The architecture of layers within a neural network is pivotal in defining the model's capability. Layers are typically organized in a sequence, from the input layer to several hidden layers, culminating in an output layer. The input layer serves as an entry point, sourcing data into the network. Hidden layers, often many in count within deep learning, extract and refine features through intricate connections and diverse activation functions. These layers are where the model truly learns by adapting weights and biases during training. The output layer provides the final prediction or classification. Designing an optimal layer architecture necessitates balancing depth and width, ensuring the model remains computationally feasible while being adept at capturing essential data representations. A well-structured layer configuration is thus essential for achieving high performance and generalizing effectively across unseen data. Types of neural networks. Feedforward networks. Feedforward networks represent the fundamental concepts of neural network models. These networks are structured in a way where data moves in a single direction, from the input nodes, through hidden layers, and finally to the output nodes, without any loops or cycles. The simplicity of feedforward networks makes them an excellent starting point for understanding more complex architectures. They find substantial application in tasks such as pattern recognition and classification. In these networks, each node of one layer connects to every node of the following layer, which allows them to model complex nonlinear relationships in data. Recurrent neural networks. Recurrent neural networks, RNNs, differentiate themselves by incorporating cycles in the network, which enables them to maintain a form of memory regarding past computations. This capability makes RNNs particularly suited to sequential data, such as time series prediction, language modeling, and other scenarios where context and order are crucial. Each hidden state in an RNN stores information about the previous inputs through cycles and feedback loops. However, RNNs can struggle with long-term dependencies due to issues such as vanishing gradients, which lead to more complex models like long short-term memory, LSTM, and gated recurrent unit, GRU. Convolutional neural networks. Convolutional neural networks, CNNs, are highly effective for spatial data processing, especially images. A CNN's ability to detect and recognize patterns with translation invariance makes it the architecture of choice for computer vision tasks. The uniqueness of CNNs lies in their convolutional layers, where they apply a set of learnable filters to the input data to extract hierarchical features. Pooling layers follow convolutional layers to reduce dimensionality, emphasizing important features while controlling overfitting. The arrangement of convolutional and pooling layers allows CNNs to learn increasingly complex patterns with depth, making them indispensable for applications ranging from image classification to texture analysis and beyond. Training neural networks. Data preprocessing techniques. In the realm of neural networks, data preprocessing holds a quintessential role. Properly processed data not only enhances model accuracy but also accelerates the learning process. Techniques often involve normalization, which scales features to a specific range to ensure uniformity and improve network convergence. Standardization is another commonly utilized method. It centers the data around zero and scales with unit variance, thus aiding in stabilizing the learning process. Furthermore, handling missing values through imputation or removal ensures the integrity and completeness of the dataset. These techniques collectively contribute to a well-prepared dataset, forming the foundation for effective neural network training. Backpropagation algorithms. Backpropagation stands as a cornerstone in the training of neural networks. It is an efficient algorithm used to update the weights in the network, facilitating the minimization of error through gradient descent. The process works by propagating the error backward from the output to the input layer, adjusting the weights iteratively. This iterative process uses the chain rule to efficiently compute gradients, ensuring the network learns from its mistakes. Variants such as stochastic, mini-batch, and batch gradient descent offer flexibility in choosing the most suitable approach depending on computational resources and the size of the dataset. Such algorithms are indispensable, as they provide the means to optimize neural networks for improved performance. Optimization methods. Optimization methods play a vital role in enhancing the performance of neural networks by efficiently minimizing the error function. Traditional methods like stochastic gradient descent, SGD, serve as the backbone of most neural network training, given their simplicity and effectiveness. Advanced optimizers such as ADAM, RMS-Prop, and AdaGrad introduce adaptive learning rates, which dynamically adjust during training to accelerate convergence. These methods mitigate issues like vanishing and exploding gradients, thus providing stability in learning deep networks. They incorporate momentums and running averages to overcome local minima and saddle points. Collectively, these optimization strategies ensure that neural networks do not only converge but do so efficiently, balancing speed and accuracy, key to state-of-the-art model development. Applications of neural networks. Natural language processing and neural networks. In the domain of natural language processing, NLP, neural networks have become quintessential. These models, particularly recurrent neural networks, RNNs, and transformers, process and generate human language with remarkable precision. By capturing patterns within large datasets, neural networks improve machine translation, sentiment analysis, and even text summarization. Transformers, such as BERT and GPT, leverage attention mechanisms to better understand context, thereby enhancing linguistic predictions and aiding in creating more natural interactions between humans and machines. Neural networks in computer vision. Neural networks have tremendously advanced the field of computer vision. Convolutional neural networks, CNNs, for instance, have revolutionized image and video analysis. By mimicking the human visual system, CNNs excel at identifying objects, detecting features, and categorizing images. This capability is crucial across multiple applications, including facial recognition systems, autonomous vehicles, and surveillance technologies. The hierarchical structure of CNNs allows them to capture complex features, making them indispensable tools for image classification and pattern recognition tasks. Use cases in healthcare. In healthcare, neural networks offer transformative opportunities in diagnosis, treatment planning, and personalized medicine. They analyze vast amounts of medical data, enabling early detection of diseases through pattern recognition in medical imaging such as MRIs and CT scans. Neural networks also facilitate the development of predictive models for patient outcomes and the discovery of potential treatment pathways. For instance, neural networks assist in predicting the likelihood of disease progression, which aids clinicians in making informed decisions. Additionally, these models support the advancement of drug discovery by analyzing chemical interactions and predicting compound efficacy, thus accelerating the development of new treatments. Challenges in neural network implementation. Overfitting and underfitting in models. Neural networks, while powerful, often face challenges related to model fitting. Overfitting occurs when a model learns the training data too well, capturing noise along with relevant patterns. This results in a model that performs well on training data but poorly on unseen data. Conversely, underfitting happens when a model is too simplistic, failing to capture the underlying distribution. This challenge necessitates careful model selection, regularization techniques, and validation methods to achieve a balance, ensuring that the model generalizes well across diverse datasets. Computational costs. Implementing neural networks can be computationally expensive. The complexity and depth of these models require substantial computational resources, often necessitating high-performance hardware such as GPUs. This leads to increased electricity consumption and demands significant computational power for both training and deployment stages. Moreover, as models grow in complexity, the time required for training can exponentially increase, posing challenges in timely execution. These constraints emphasize the importance of optimizing algorithms and infrastructure to manage costs effectively while maintaining performance. Data quality issues. The performance of neural networks heavily depends on the quality of data used for training. Data that is noisy, incomplete, or biased can significantly degrade model performance, leading to inaccurate predictions. Furthermore, imbalanced datasets can skew model outcomes, as the network may become biased toward the majority class. To overcome these issues, it is crucial to invest in data preprocessing steps, including cleaning, normalization, and augmentation. This ensures that the network receives high-quality, representative data, enhancing model reliability and validity in predictive tasks. Effective strategies must be implemented to continually assess and improve data quality, enabling the development of robust and dependable models. In conclusion, Addressing these challenges in neural network implementation requires a multifaceted approach. Combining advanced algorithmic strategies with efficient resource management and comprehensive data handling protocols is essential. By doing so, practitioners can harness the full potential of neural networks, delivering transformative outcomes across various domains. The ongoing evolution in this field promises innovative solutions to these challenges, paving the way for further advancements and applications. Future prospects of neural networks reducing computational complexity. One significant future prospect of neural networks is the potential to reduce computational complexity. As neural networks grow in size and capacity, their demand for computational resources increases. Researchers are exploring various methods to streamline these computations. One approach focuses on developing algorithms that reduce redundant operations within the network. By employing techniques such as pruning and quantization, models can maintain their performance while executing fewer calculations. This not only speeds up processing but also reduces energy consumption, making neural networks more sustainable and accessible for a variety of applications. Innovations in model efficiency in tandem with reducing computational complexity. There is a burgeoning interest in enhancing model efficiency. Innovations are focusing on optimizing both the architecture and the training processes of neural networks. Techniques such as transfer learning allow models to apply knowledge from previous tasks to new ones, effectively reducing the need for extensive dataset-specific training. Additionally, Neural Architecture Search (NAS) is gaining traction. This approach automates the design of neural networks tailored to specific tasks or constraints, thus improving efficiency. As these methods mature, they promise to make neural networks more versatile and resource economic across diverse contexts. Neural networks in quantum computing. The intersection of neural networks and quantum computing represents a frontier of technological advancement. Quantum computing, with its capacity to process information at unprecedented speeds, offers opportunities to transform how neural networks are utilized. Neural networks could benefit from quantum computing's ability to handle vast amounts of data in parallel, significantly enhancing their computational power. This synergy is anticipated to solve problems that are currently intractable with classical computing. For instance, quantum neural networks could accelerate advancements in areas such as cryptography, material science, and complex system simulations. While still in the nascent stages, the integration of neural networks into the quantum computing domain underscores a promising horizon that could redefine the potential of computational technologies as we advance further into this century. Ethical considerations in neural network deployment. Bias in neural network predictions. Neural networks, while powerful, are susceptible to bias. Bias arises when the data used to train these networks is not representative of the entire population. This can result in skewed predictions that favor one group over another. For example, if a neural network is trained primarily on data from one demographic group, its predictions may not generalize well to other groups, potentially leading to unfair outcomes in applications such as hiring or lending. Ensuring diversity in training datasets is crucial. Researchers and practitioners must continuously evaluate models against biases and employ techniques to mitigate them. Bias audits, transparency in algorithm design, and the inclusion of diverse perspectives during model development are necessary practices to reduce this issue. Privacy concerns. Privacy is a significant concern in the deployment of neural networks. These models often require vast amounts of data to function effectively, some of which may be sensitive personal information. Without proper safeguards, this data can be exposed to unauthorized access and misuse, posing risks to individuals' privacy. Encryption and advanced data anonymization techniques are essential to protect sensitive data during both training and deployment phases. It is imperative for organizations to adhere to data privacy laws and regulations, ensuring they have robust security measures in place. Furthermore, informing users about data collection practices and seeking their consent reinforces trust and enhances transparency. Regulatory compliance. Regulation plays a crucial role in the ethical deployment of neural networks. legal frameworks and industry standards guide organizations in the responsible use of artificial intelligence technologies. Compliance with these regulations ensures that neural networks are deployed in a manner that respects human rights and societal norms. In many jurisdictions, there are specific guidelines on data handling, bias prevention, and transparency in automated decision-making processes. Organizations must stay informed about regional regulations and industry standards to remain compliant. This includes conducting comprehensive impact assessments and maintaining detailed records of model development and decision-making processes to demonstrate accountability. Interdisciplinary approaches to neural network research integrating neuroscience and AI. The intersection of neuroscience and artificial intelligence, AI, has become a fertile ground for innovation in neural network research. Both fields aim to understand and simulate intelligent behavior, yet they approach the challenge from differing perspectives. Neuroscience seeks to unravel the complexities of biological neurons and cognitive processes, whereas AI endeavors to recreate this intelligence through computing systems. By integrating insights from neuroscience into AI models, researchers can develop more robust neural networks that mirror human-like problem-solving and learning capabilities. This interdisciplinary synergy not only advances AI technologies but also offers neuroscientists novel methodologies to interpret brain data. Collaboration between academia and industry. Collaboration between academic institutions and industry players is crucial for propelling neural network research to new heights. Academia provides a rigorous scientific foundation and the freedom for exploratory research, which is vital for foundational advancements in neural networks. Conversely, industry possesses resources and platforms to scale these innovations and apply them to real-world applications. When researchers and corporations join forces, they can swiftly translate academic theories into practical tools and systems. Moreover, these partnerships often pave the way for the creation of specialized research facilities and the development of talent pools equipped with cutting-edge skills, fostering an ecosystem that facilitates continuous innovation. The role of open-source communities. Open-source communities have played a transformative role in neural network research by democratizing access to advanced tools and resources. These communities provide a collaborative space where researchers, developers, and enthusiasts from various disciplines can contribute to and refine existing technologies. Open-source platforms like TensorFlow and PyTorch have become foundational in the neural networks field, allowing researchers to implement and experiment with complex models without incurring prohibitive costs. Such openness accelerates innovation, as findings and improvements are shared freely, enabling rapid iteration and refinement. Furthermore, these communities often set standards and benchmarks that guide the field's collective progress, ensuring a cohesive yet diverse development trajectory. Key tools and frameworks for neural networks: TensorFlow and PyTorch. TensorFlow and PyTorch stand prominently as leading frameworks in the neural network space, catering to diverse needs in research and deployment. TensorFlow, developed by Google, offers a robust ecosystem that integrates smoothly with Google's suite of tools while supporting both CPU and GPU computing. Its flexible architecture is designed for production environments, providing a comprehensive platform for both model building and deployment. PyTorch, an offering from Facebook, is favored for its dynamic computational graph, which allows for more intuitive model experimentation. Researchers appreciate its straightforward interface and the seamless integration with Python, enabling efficient debugging and iterative improvement. These frameworks not only reduce the complexity involved in script writing but also optimize the performance of neural networks by simplifying the implementation of complex computations. Keras for rapid prototyping. Keras serves as an invaluable tool for researchers and developers seeking rapid prototyping capabilities. Built on top of TensorFlow, Keras operates as a high-level neural networks API, specifically aimed at enabling quick experimentation without sacrificing power or flexibility. Its user-friendly interface manages to abstract the complexities inherent in model development, making it accessible to both novices and experts. Keras supports easy and fast prototyping through its modular nature, where building and executing neural network models require minimal code. The simplicity of Keras does not impede its efficacy. It supports convolutional networks, recurrent networks, and the combination of the two, allowing users to swiftly translate research ideas into functioning models. Emerging tools in neural network development. In the rapidly evolving field of neural network development, emerging tools are continually influencing the landscape. Among these are frameworks emphasizing efficiency and usability for both established and novel neural network architectures. Tools like JAX, which leverages the powerful automatic differentiation capabilities of XLA, and ONNX, which focuses on interoperability across different frameworks, represent the increasing importance of flexibility in model deployment. These emergent technologies are designed to meet the growing demand for solutions that are not only effective but also adaptable to the shifting needs of the research and industrial communities. As the toolkit for neural networks continues to expand, adaptability and scalability remain pivotal properties these tools strive to provide. Measuring neural network performance evaluation metrics and benchmarks. Evaluating neural network performance requires a systematic approach, using established metrics and benchmarks. Common metrics include accuracy, precision, recall, and F1 score. These metrics provide insights into the performance of classification tasks by quantifying the correctness of predictions. The accuracy metric indicates the proportion of correctly predicted observations, while precision and recall assess the quality of positive predictions and the model's ability to identify all relevant instances, respectively. The F1 score combines precision and recall into a single measure, making comparisons easier. Benchmarks offer standard datasets and tasks for measuring neural networks against others. These provide a framework for objectively assessing performance and can highlight a model's strengths and weaknesses. Real-time testing environments. Real-time testing environments put neural networks through practical scenarios to evaluate their performance under actual operating conditions. This is critical for applications with time-sensitive outputs, such as autonomous vehicles or financial trading systems, where delay or inaccuracies could lead to significant consequences. These testing environments simulate real-world challenges by incorporating unexpected events and fluctuating inputs, ensuring that the neural networks can adapt and perform consistently. The effectiveness of real-time testing depends on its ability to replicate true-to-life complexities. This involves using advanced simulations and engaging with unpredictable data streams. Continuously monitoring performance in these environments helps in refining models to achieve higher robustness and reliability. Interpreting neural network outputs. Interpreting the outputs of neural networks is essential in determining the trustworthiness and practical impact of their predictions. Neural networks, especially deep learning models, can act as black boxes with intricate operations that are not immediately understandable. It is crucial for researchers and practitioners to demystify these outputs to ensure reliability. Several techniques aid in interpreting these results. Visualization tools can map how inputs translate to outputs, illuminating hidden processes. Salience maps or attention visualization help understand feature importance. Explainable AI methods can simplify interpretation, providing insights into decision-making processes. Such transparency is vital for aligning neural network outputs with ethical guidelines and user expectations, guiding improvement and fostering trust in AI systems.